Hi everyone. So today we're going to proceed with our next topic, which is the main memory. So the last time we discussed about how CPU can be shared by a set of processes. And we also discussed the topic regarding CPU scheduling, wherein we can improve both the utilization of the CPU and at the same time the speed of the computer's response to its users. However, to realize the increase in performance, we should keep many processes inside the memory. As we all know, all the processes, all the program's instructions are kept in the memory, and then it will be fetched by the CPU for execution. So therefore we have what we call a shared memory. So in this particular chapter, we're going to discuss various ways to manage memory, and you will see that each approach has its own advantages and disadvantages. So our outline will cover the following topics. So we'll have the background, and then contiguous memory allocation. We'll also discuss about paging, and then the structure of the page table. We will also discuss swapping, and then we will give some examples of the different architectures, such as the Intel 32 and 64-bit architectures and the ARM version 8 architecture. The objectives of the topic is that at the end of this session you will be able to provide a detailed description of various ways of organizing memory hardware, and then you should be able to discuss various memory management techniques, and then provide a detailed description of the Intel Pentium, which supports both pure segmentation and segmentation with paging. So for our background, if you remember from our first module, we discussed that the memory is important in the operation of many modern computer systems. While memory is composed of a large array of bytes, and each with its own address, we all know that the CPU fetches instruction from the memory according to the value of the program counter, and these instructions may cause additional loading from and storing to specific memory addresses. So for example, a typical instruction execution cycle, for example, it will first fetch an instruction from the memory, and then the instruction is decoded and could cause operands to be fetched from the memory. Now, after the instruction has been executed on the operands, results may be stored back in the memory. So the memory unit will only see a stream of memory addresses. It doesn't know how they are generated. For example, the memory doesn't know that they are generated by the instruction counter, indexing, indirection, literal addresses, and so on. The memory doesn't also know what they are. For example, if they are instructions or if they are data. So accordingly, we can ignore how a program generates a memory address. So we are only interested in the sequence of memory addresses generated by running the program. So we will begin our discussion by covering several issues that are important to managing memory. For example, basic hardware, the binding of symbolic or virtual memory addresses to actual physical addresses, and the distinction between logical and physical addresses. So we should remember that the only storage devices that the CPU can access are the main memory and the registers. So as such, the main memory and the registers are directly accessed by the CPU. So every time that the CPU fetches an instruction, it directly access it or fetch it from the main memory or from the registers. However, as I have mentioned, what the memory only sees are a stream of addresses, such as in this format, addresses plus read requests and addresses plus data and write requests. So if you remember, in our previous courses, we have already identified that the registers are storage that are built into each CPU core, and they are generally accessible within one CPU clock, or we call it one cycle. And for example, some CPU cores can decode instructions and perform simple operations on register contents at the rate of one or more operations per clock tick. So the same cannot be said of the main memory because they are different. The main memory is accessed via a transaction on the memory bus. Sometimes completing a memory access, in many cases, it will take many cycles of CPU clock, no? The main memory can take many CPU clock or many cycles to be able to complete a memory access. So in such cases, the processor normally needs to stall, no? So it will cause a stall on the CPU, since it doesn't have the data required to complete the instruction that it is executing. So the remedy is to add fast memory between the CPU and the main memory. So what is that remedy? It's typically a CPU chip for fast access, and that is what we call a cache. So the cache sits between the main memory and the CPU registers, which we will describe later. We already described this before, that a cache is a cache which is built into the CPU, a hardware that automatically speeds up the memory access without any operating system control. Now, for proper system operation, we must protect the operating system from access by user processes, as well as protect user processes from one another. So this protection must be provided by the hardware, because the operating system doesn't usually intervene between the CPU and its memory access. Therefore, protection of memory is required to ensure correct operation. In terms of protection, we need to make sure that each process has a separate memory space. So the separate per process memory space protects the processes from each other, and very important to having multiple process or processes loaded in memory for concurrent execution. So how do we do the protection? So to separate memory spaces, we need the ability to determine the range of the legal addresses that the process may access, and to ensure that the process can only these legal addresses. So we can provide this protection by using two registers. Usually, it's a base and a limit. So in the illustration, although the letters are not clear here, this is an illustration of a base and a limit register which defines a logical address space, wherein, for example, in this memory we have the operating system here, and these are the different processes. So each processes, including the operating system, has its appropriate memory addresses. But for each process, so that each process will be protected by other processes, they are bounded by the base. For example, in this process, this is the base, and the extent of it will be called base plus the limit. So that is what we call. So the base register holds the smallest legal physical memory address, and the limit register specifies the size of the range. For example, if the base register holds, for example, 3040, and the limit register is 120,900, so the program can legally access all addresses from 300,040 through 420,939. So it will be the addition of the two addresses. The protection of the memory space is accomplished by having the CPU hardware compare every address generated in user mode with the registers, and any attempt by a program executing in the user mode to access the operating system memory or other users' memory results in a trap to the operating system, and this will be treated as an attempt and will be a fatal error. As shown in this figure, you will see a trap to operating system wherein an illegal addressing error occurred. For the address binding, usually a program resides on a disk as a binary executable file, and to be able to run the program must be brought into a memory and placed within the context of a process, where it becomes eligible for execution on an available CPU. So as the process executes, it accesses the instructions and data from the memory. Eventually, the process terminates and its memory is reclaimed for use by other processes. So definitely, all the programs on the disk ready to be brought into a memory to execute, they are all placed in an input queue. So for example, it can be loaded in a memory address such as 0000. However, it doesn't mean that if it is loaded at 0000, it doesn't mean that the first address of the user processes will always be 0000. So you will see later how the operating system actually places a process in the physical memory. In most cases, a user program goes through several steps, some of which may be optional before being executed. So the addresses may be represented in different ways during these steps. So the addresses in the source program, for example, can be generally symbolic. For example, they can be a variable count. And a compiler typically binds, they typically bind, which means these symbolic addresses can be a relocatable addresses, such as, for example, 14 bytes from the beginning of this module. So the linker or the loader in turn binds the relocatable addresses to absolute addresses. So it will become 74,014 instead of 14 bytes only. So each binding maps one address space to another. And classically, the binding of instruction and data to memory addresses can be done at any step along the way. So in the figure below, you will see the different steps, the multi-step processes of a user program. As we mentioned, if there is a source program, for example, that is being compiled or sent to the compiler or assembler, so that's going to be what we call the compile time. And then when that process will proceed to the next part, which is the creation of the module, it will proceed to the next part, which is the linkage editor. And this part of the linkage editor is used to load all the modules needed for the loader to be processed. From the linkage editor up to the loader, so that is what we call the load time. From the loader, the program will be executed, thus it will become the execution time. So if we will recall from here, these are what we call the binding instructions of the data to memory. So these instructions can happen at different times or different stages, such as the compile time that we have seen from the image, wherein if memory location known a priori, absolute code can be generated, and it must recompile code if starting or location changes. So that means if you know at compile time where the process will reside in memory, then the absolute code can be generated. For example, if you know that a user process will reside starting at location A, then the generated compiler will start at that location and extend up from there. If at some later time the starting location changes, then it will be necessary to recompile this code. So it happens during the compile time. The next is the load time, wherein it must generate a relocatable code if the memory location is not known at the compile time. So that means if it is not known at compile time where the process will reside in the memory, then the compiler will have to generate the relocatable code. And in this case, final binding is delayed until load time. Now, if the starting address changes, we need only to reload the user code to incorporate this change value. The last is the execution time, where if the process can be moved during each execution from one segment to one another, then binding must be delayed until runtime. And special hardware must be available for the scheme of work. For example, it will be needing to a hardware to support for address maps such as the base and the limit registers. Okay, these are some terms that we need to understand, which will be covered here. So the address generated by the CPU is commonly referred to as the logical address. Remember that, okay? That's the address generated by the CPU. It's also called as the virtual address. Now, the address seen by the memory unit is what we call the physical address. So, the difference between the two is that the logical address are generated by the CPU, while the physical address are the addresses seen only by the memory unit. So the logical and physical addresses are the same in compile time and load time address binding schemes. They are typically the same. So the logical or the virtual and physical addresses will only differ in execution time address binding scheme. So remember, they are the same in the compile time and the load time address binding schemes, but they are different. They will become different during the execution time address binding scheme. So definitely what we need to understand here is the logical address space and the physical address space, wherein logical address space is the set of all physical or set of all logical addresses generated by a program, while the physical address space is the set of all physical addresses generated by a program. Now, inside the computer system, we had what we call a memory management unit. The purpose of the function of the memory management unit is to run time maps with virtual to physical addresses. So basically, what it does is to run time maps the virtual to physical addresses coming, wherein the logical addresses will be mapped to its physical addresses before it proceeds to the physical memory. And there are many methods that are possible to do that, but for the time being, we illustrate this mapping with a simple memory management unit scheme that is a generalization of the base register scheme. Now, the base register scheme or the base register is now called a relocation register, wherein the value in the relocation register is added to every address generated by a user process at the time the address is sent to memory. For example, if the base is at 14,000, then an attempt by the user to address location 0 is dynamically relocated to location 14,000. An access to location 346 is mapped to location 14,346. So it's like typically this logical address will be addressed to the relocation register, which will give us the physical address of 14,346. So the base is 1400 or 14,000. Then if there is an attempt by the user to address the location 0, which is dynamically relocated to this location 14,000, the access to location 346 will then be mapped to location 14,346. So the user program never accesses the real physical addresses. The program can create a pointer to location 346, store it in the memory, manipulate it, and compare it with other addresses, all as the number 346. So only when it is used as a memory address is it relocated relative to the base register. So the user program deals with logical addresses, and the memory mapping hardware converts the logical address into physical addresses. And this form of execution time binding was already discussed. Okay, the final location of a reference memory address is not determined until the reference is made. So definitely, we now have two different types of addresses. The logical addresses in the range of 0 to the maximum address that it can have, and the physical, or we call it the real physical addresses. So we have the logical addresses from 0 to max, and the physical addresses in the range of the, for example, R, which is the real, plus 0 to R plus max for a base value of the R. Okay? So the user program generates only logical addresses and thinks that the process runs in memory location from 0 to max. However, these logical addresses must be mapped to physical addresses before they are used. So the concept of a logical address space that is bound to a separate physical address space is central to proper memory management. So far, it has been necessary for the entire program and all data of process to be in the physical memory for the process to execute. So we have discussed all about that. But the size of a process has thus been limited to the size of the physical memory. Now, to obtain better memory space utilization, we can use what we call a dynamic loading. With dynamic loading, a routine is not loaded until it is called. Remember that. A routine is not loaded until it is called. So all the routines are kept on the disk in a relocatable load format, and the main program is loaded into memory and is executed. When a routine needs to call another routine, the calling routine is executed, or the calling routine first checks to see whether the other routine has been loaded. If it has not, the relocatable linking loader is called to load the desired routine into memory and to update the program's address tables to reflect this change, and then control is passed to the newly loaded routine. So the advantage or the advantages of dynamic loading is that a routine is loaded only when it is needed. And this method is particularly useful when large amounts of code are needed to handle infrequently occurring cases such as error routines. So in such situations, although the total program size may be large, the portion that is used may be much smaller. So dynamic loading does not require special support from the operating system, and it is the responsibility of the users to design their programs to take advantage of the method. Meanwhile, the OS or the operating system may help the provider or the programmer by providing library routines to implement dynamic loading. Aside from dynamic loading, we have what we call dynamic linking. Dynamically linked libraries, or DLLs for short, are system libraries that are linked to user programs when the programs are run. And some operating system, they support static linking, in which the system libraries are treated like any other object module, and they are combined by the loader into binary program image. So dynamic linking, in contrast, is similar to dynamic loading. However, rather than loading, which is postponed until execution time, the linking is postponed until execution time. And this feature is usually used with system libraries such as, for example, the standard C language library. Without this facility, each program on a system must include a copy of its language library in the executable image. So the requirement not only increases the size of an executable image, but also may waste main memory. A second advantage of DLLs is that these libraries can be shared among multiple processes, so that only one instance of the DLL will be in the main memory. And for this reason, DLLs are also known as shared libraries, and they are very extensively used in Windows and in Linux systems. The main memory must accommodate both the operating system and the various user processes. So we therefore need to allocate the memory efficiently in the most efficient way as possible. And this section will explain one early method, which is the contiguous allocation or contiguous memory allocation. The memory is usually divided into two partitions, one for the operating system and one for the user processes. So we call it the resident operating system, which is usually held in a low memory with interrupt vector, and the user processes are usually held in the high memory. So these are locations in the memory. We call it low memory and we call it the high memory. And each process contained in a single contiguous section of the memory. However, nowadays, many operating systems, including Linux and Windows, they are now placing the operating system in the high memory, and we will discuss only that situation. So as we have discussed, the relocation registers is used to protect user processes from each other and from changing operating system code and data. So from the illustration, we have learned that, for example, if the relocation register contains the range or contains the value of the smallest physical address, the limit register contains the range of a logical address. So in this case, the base register contains the value of the smallest physical address, and the limit register contains the range of the logical addresses. Each logical address must be less than the limit register. So who maps the logical address dynamically? It is the memory management unit, which then can allow actions such as kernel code being transient and the kernel from changing its size. So this is the concept of the memory protection. Like for example, when the CPU scheduler selects a process for execution, the dispatcher loads the relocation and limit registers with the correct values as part of the context switch. Because every address generated by the CPU is checked against these registers, we can protect both the operating system and the other users' programs and data from being modified by this running process. So the relocation register scheme provides an effective way to allow the operating system size to change dynamically, and this flexibility is desirable in many situations. For example, the operating system contains code and buffer space for device drivers. So if a device driver is not currently in use, it makes little sense to keep it in the memory. Instead, it can be loaded into memory only when it is needed. Likewise, when the device driver is no longer needed, it can be removed and its memory allocated for other needs. Now let's proceed with memory allocation. One of the simplest methods of allocating memory is to assign processes to variably sized partition in memory, where each partition may contain exactly one process. So in this, we call it variable partition scheme, where the operating system will keep a table indicating which parts of the memory are available and which are occupied. So initially, all memory is available for user processes and is considered one large block of available memory, which is considered to be the whole. Eventually, as you will see, memory contains a set of holes of various sizes. So from this example, you will see the memory initially is fully utilized, containing process 5, process 8, and process 2. So when the process 8 leaves, there is one contiguous hole. Ito, this one. This is the contiguous hole. And later on, process 9 arrives and is allocated memory. Then process 5 departs, resulting in two non-contiguous holes. So as processes enter the system, the operating system takes into account the memory requirements of each process and the amount of available memory space in determining which processes are allocated memory. So when a process is allocated space, it is loaded into a memory where it can then compete for CPU time. And when the process terminates, it releases the memory which the operating system may then provide to another process. So what happens when there isn't sufficient memory to satisfy the demands of an arriving process? One option is to simply reject the process and provide an appropriate error message. So alternatively, we can place such processes into a wait queue. Like when memory is later released, the operating system checks the wait queue to determine if it will satisfy the memory demands of a waiting process. So in general, as mentioned, these memory blocks available comprise a set of holes of various sizes scattered throughout the memory. And when a process arrives and needs memory, the system will search for the set of a hole that is large enough for this process. Okay? Now, if the hole is too large, it will be splitted into two parts. And one part is allocated to the arriving process, and the other is returned to the set of holes. So when a process terminates, it releases its block of memory, which is then placed back in the set of holes. But what if the new hole is adjacent to other holes? These adjacent holes are merged to form one larger hole. And this procedure is a particular instance of the general dynamic storage allocation problem, which concerns how to satisfy a request of, let's say, a request of size n from a list of free holes. There are many solutions to this problem. One solution is what we call the first fit, the best fit, and the worst fit strategies. So they are all strategies where the ones most commonly used to select a free hole from the set of available holes. The first fit allocates the first hole that is big enough. Searching can start either at the beginning of the set of holes or at the location where the previous first fit search ended. And then we can start searching as soon as we find a free hole that is large enough. For the best fit, we allocate the smallest hole that is big enough. But we must search the entire list unless the list is ordered by size. And this strategy produces the smallest leftover hole. The worst fit allocates the largest hole. Again, we must search the entire list until it is sorted by size. However, this strategy produces the largest leftover hole, which may be more useful than the smaller leftover hole from a best fit approach. So simulations have shown that both first fit and best fit are better than worst fit in terms of decreasing time and storage utilization. And neither first fit nor best fit is clearly better than the other in terms of storage utilization, but first fit is generally faster. Now, both the first fit and best fit strategies for memory allocation suffer from what we call external fragmentation. And what is this external fragmentations? As processes are loaded and removed from the memory, the free memory space is broken into little spaces or little pieces. External fragmentation exists when there is enough total memory space to satisfy a request, but the available spaces are not contiguous. In that case, storage is fragmented into a large number of small holes, and this fragmentation problem can be severe. In worst case, we could have a block of free or wasted memory between every two processes. And if all these small pieces of memory were in one big free block instead, we might be able to run several more processes. So whether we are using the first fit or best fit strategy, they can also affect the amount of fragmentation. First fit is better for some systems, but best fit is better for others. Another factor is which end of a free block is allocated, which is the leftover piece. So the one on the top or the one on the bottom, no matter which algorithm is used, however, external fragmentation will be a problem. So depending on the total amount of memory storage and the average process size, external fragmentation may be a minor or a major problem. And statistical analysis of first fit, for instance, reveals that even with some optimization, given for example n number of blocks allocated, another 50% or 0.5 of the n number of blocks are lost to fragmentation. So that will be 1/3 of a memory may be unusable, and this property is known as the 50% rule. One solution to the problem of external fragmentation is compaction. So the goal is to shuffle the memory contents so as to place all the free memory together in one large block. And compaction is, however, compaction is not always possible. If relocation is static, for example, and is done at assembly or load time, compaction cannot be done. Okay? So as it was mentioned here, shuffle memory contents to place all memory together in one large block. But it's only possible if relocation is dynamic, and it is done during execution time. Okay? Another possible solution to external fragmentation problem is to permit the logical address space of processes to be non-contiguous, which will allow a process, for example, to be allocated physical memory wherever such memory is available. And this strategy is what we call paging. Paging is the most common memory management technique for computer systems. And paging will be described here, no? So in memory management, as we have discussed so far, memory management required the physical address space of a process to be contiguous. So paging, as I have said, is a memory management scheme that permits process physical address space to be non-contiguous, and paging avoids external fragmentation and the associated need for compaction, two problems that plague contiguous memory allocation. Because it offers numerous advantages, paging in its various forms is used in most operating systems, from those for large servers through those for mobile devices. And paging is implemented through cooperation between the operating system and the computer hardware. Now, the basic method for implementing paging involves breaking physical memory into fixed size blocks called frames. So that is the meaning of the term frames. So remember that a frame is the breaking of physical memory into fixed sized blocks. And if you break the logical memory into blocks of the same size, it will now be called pages. So that's the difference between the two. When you break or divide the physical memory into fixed size blocks, it is called the frames. But when you divide the logical memory into blocks of the same size, it's called pages. So when a process is to be executed, what happens? Its pages are loaded into any available memory frames from their source. It can be a file system or a backing store. So the backing store is divided into fixed size blocks that are the same as the memory frames or clusters of multiple frames. And this rather simple idea has great functionality. For example, the logical address space is now totally separate from the physical address space. So a process can have a logical 64-bit address space even though the system has less than 2 raised to 64 bytes of physical memory. So every address generated by the CPU is divided into parts. The first part is what we called a page number, and the second part is what we call a page offset. So the page number is used as the index into a per process page table. Alright? So the page table contains the base address of each frame in physical memory, and the offset is the location in the frame being referenced. Thus, the base address of the frame is combined with the page offset to define the physical memory address. So the paging memory model or the paging model of memory is shown here. As you can see, this is the paging model of the logical and the physical memory. And this is the paging hardware. Now, in the paging model of logical and physical memory, the following outlines the steps taken by the memory management unit to translate a logical address generated by the CPU to a physical address. The first thing that it does is to extract the page number P and use it as an index into the page table. Number 2, it extracts the corresponding frame number F from the page table, and then it replaced the page number P in the logical address with the frame number F. So as the offset D does not change, it is not replaced, and the frame number and offset now comprise the physical address. So the page size, like the frame size, is defined by the hardware. So usually the size of a page is a power of 2, typically varying between 4 kilobytes and 1 gigabyte per page, depending on the computer architecture. So the selection of a power of 2 as a page makes the translation of the logical address into a page number and page offset particularly easy. If the size of the logical address space is 2 raised to m and the page size is 2 raised to n, then the high order m minus n of the bits of a logical address designate the page number, and the n low order bits designate the page offset. Thus, the logical address is as follows. So this is the illustration of the physical address. So if the size of the logical address is 2 raised to m and the page size is 2 raised to n, then the n low order bits designated the page offset, alright, and the n low order bits designate the page offset. So this is what we call the physical address. As a concrete example, consider the memory in this figure where the logical address is n is equal to 2 and m is equal to 4. So using a page size of 4 bytes and a physical memory of 32 bytes or 8 pages, we can show how the programmer's view of memory can be mapped into physical memory. Logical address 0 is page 0. Right, so this is logical address 0, it's in page 0, and offset 0. Indexing it into the page table, this is the page table, we find that page 0, this is page 0, is in frame 5. Thus, logical address 0 maps to physical address, which is equal to 5 multiplied by 4, because they have the size of 4 bytes. So 5 times 4 plus 0, which is the page 0, that will be equivalent to 20. Now, if we are looking for the logical address 3, for example, the page is in page 0 here in the logical memory. You will see that the logical address 3 is in page 0 and the offset is 3. It maps to the physical address 5 multiplied by 4 bytes plus 3. That means the address or the physical address is 23. So that is the physical address. Now, when we use a paging scheme, we have no external fragmentation, and any free frame can be allocated to a process that needs it. However, we may have some internal fragmentation. Notice that the frames are allocated as units. So if the memory requirements of a process do not happen to coincide with page boundaries, the last frame allocated may not be completely full. For example, if a page, in this example, a page size is 2048 bytes. So the process of 72,766 bytes will need 35 pages plus 186 bytes, and it will be allocated 36 frames, resulting in internal fragmentation of 2048 minus 1086, which is equal to 962 bytes. In the worst case, a process would need n number of page plus 1 byte. Alright? So it would be allocated n plus 1 frames, resulting in internal fragmentation of almost an entire frame. Now, inside the memory, we have what we call a page table, no? And it is being kept inside the main memory. And there is also a pointer to the page table which stores the other register values, like for example the instruction pointer. And this points to the page table, which is what we call the page table base register. Now we have another term here which indicates the size of the page table. It's called the page table length register. And in this scheme, every data or instruction access requires two memory accesses, one for the page table and one for the data or the instruction. So the two memory access problem can be solved by the use of a special fast lookup hardware cache called transaction or translation look aside buffers, or TLBs, also called associative memory. Although storing the page table in memory can yield faster context switches, it may also result in slower memory access times. Suppose we want to access location I. Alright? We must first index into the page table using the value in the PTBR offset by the page number for I. And this task requires one memory access, and it provides us with a frame number which is combined with the page offset to produce the actual address. So we can then access the desired place in the memory. With this scheme, the two memory accesses are needed to access the data, one for the page table entry and one for the actual data. Thus, a memory access is slowed by a factor of 2, a delay that is considered intolerable under most circumstances. So the standard solution to this problem is to use a special small fast lookup hardware cache called TLB, or translation look aside buffer. So the TLB is associative high-speed memory, and each entry in the TLB consists of two parts: a key or tag and a value. When the associative memory is presented with an item, the item is compared with all the keys simultaneously. If the item is found, the corresponding value field is returned. So the search is fast. A TLB lookup in modern hardware is part of the instruction pipeline, essentially adding no performance penalty. And to be able to execute the search within a pipeline step, the TLB must be kept small. So usually it is between 64 to 1024 entries in size. But some CPUs implement separate instruction and data addresses, TLBs. And it can double the number of the TLB entries. Alright? It can double because those lookups occur in different pipeline steps. So we can see in this development an example of the evolution of CPU technology, where the systems have evolved from having no TLBs to having multiple levels of TLBs, just as they have multiple levels of cache. So in Ay, in some cases, some TLBs store address space identifiers or ASIDs in each TLB entry, and it uniquely identifies each process to provide address space protection for that process. The percentage of times that the page number of interest is found in the TLB is called the hit ratio. An 80% hit ratio, for example, means that we find the desired page number in the TLB 80% of the time. So if it takes 10 nanoseconds to access a memory, for example, right, then a map memory access takes 10 nanoseconds when the page number is in the TLB. But if we fail to find the page number in the TLB, then we must first access the memory for the page table and frame number 10 nanoseconds, and then access the desired byte in memory 10 nanoseconds for a total of 20 nanoseconds. So we are assuming that a page table lookup takes only one memory access, but it can take more, as we shall see. And to find the effective memory access time, or we call it EAT or effective access time, we weight the case by its probability. So what is the effective access time? It can be computed as 80% or 0.80 multiplied by 10 nanoseconds plus 20% multiplied by 20 or 20 nanoseconds, which is equal to 12 nanoseconds, implying that there is a 20% slowdown in average memory access time from 10 to 12 nanoseconds. For a 99% hit ratio, for example, which is much more realistic, we have a computation of 0.99 multiplied by 10 nanoseconds plus 0.01 multiplied by 20 nanoseconds, which is equivalent to 10.1 nanoseconds, implying that only 1% slowdown will be in the access time. In terms of memory protection, the memory protection is implemented by associating protection bit with each frame to indicate if the access is allowed. So a valid and invalid bit is attached to each entry in the page table. Valid means indicates that the associated page is in the process logical address space and is thus a legal page. Invalid indicates that the page is not in the process logical address space, or use the page table length register or PTLR, and any violations result in a trap to the kernel, which is an error in the part of the memory, and can also add more bits to indicate if read only, read write, and execute only is allowed. So in this example, in a system with a 14-bit address space, let's say from 0 to 16,383, so we have a program that should only use addresses from 0 to 10,468. So given a size of 2 kilobytes, we have the situation shown in his figure where the addresses in pages 0, 1, 2, 3, 4, 5 are mapped normally through the page table. And any attempt to generate an address in pages 6 and 7, however, will find that the valid invalid bit is set to invalid. If this happens, the computer will trap to the operating system, which is what we call the invalid page reference. So we will notice that this scheme has created a problem because the program extends only to address 10,468. So any reference beyond that address is illegal. However, references to page 5 are classified as valid. So accesses to addresses up to 12,287 are valid. Only the addresses from 12,288 up to 16,383 are invalid. And this problem is a result of the 2 KB page size and reflects the internal fragmentation of paging. An advantage of paging is the possibility of sharing common code, a consideration that is particularly important in an environment with multiple processes. So in this case, a shared code will mean one copy of read-only code or reentrant code shared among processes. For example, text editors, compilers, or Windows systems. These shared code are similar to multiple threads sharing the same process space and also useful for inter-process communication if sharing of read-write pages is allowed. So another advantage is that each process keeps a separate copy of the code and data, and the pages for the private code and data can appear anywhere in the logical address space. So here in this figure, we can see 3 processes are sharing the pages for the standard C library or libc. So although the figure shows the libc library occupying 4 spaces, such as in this image, in reality it would occupy more. So the reentrant code is non-self-modifying code. It never changes during execution. Thus, 2 or more processes can execute the same code at the same time, and each process has its own copy of registers and data to hold the data for the process execution. So the data for 2 different processes will be different. Only one copy of the standard C library need be kept in physical memory, and the page table for each user process maps onto the same physical copy of the libc. Now, to support 40 processes, we need only one copy of the library, and the total space now required is 2 megabytes instead of 80 megabytes. So we are having a significant saving. So in addition to runtime libraries such as libc, other heavily used programs can also be shared, as I mentioned, such as compilers, Windows systems, database systems, and so on. So at this point, we explore some of the most common techniques for structuring the page table, including the hierarchical paging, hash page tables, and inverted page tables. So let's start with the hierarchical paging. So most modern computer systems supports a large logical address space, which is 2 raised to 32 up to 2 raised to 64. So in such environment, the page table becomes excessively large. For example, consider a system with a 32-bit logical address space. So if the page size in such system is 4 kilobytes, so that is going to be 2 raised to 12. So if it is 1 kilobyte, then it's going to be 2 raised to 10. So the page table may consist of over 1 million entries, or 2 raised to 32 over 2 raised to 10. Alright? So if each entry is 4 bytes, then each process requires 16 megabytes of physical address space for the page table alone. So you don't want to allocate that contiguously in the main memory. And one simple solution to divide the page table into smaller units is by using hierarchical paging, hash page tables, and inverted page tables. So, as I have said, one solution is to break up the logical address into a page number consisting of, for example, one solution is to divide it into smaller pieces, and we can accomplish this division in several ways. Alright? So one way is to use a two-level paging algorithm in which the page table itself is also paged. No? In this example, you can see that the 32-bit logical address space and a size of 4 kilobytes, wherein a logical address is divided into a page number consisting of 20 bits and a page offset consisting of 12 bits. So definitely, if we have this, the page number is further divided into a 10-bit page, and this technique where we see then the page, we page the page table. This is the page table, and then we use it to get another page. So the term is used as we page the page table. So what do we have here? So we have an outer page table which is mapped to a page table, and then we map it to the physical address of the table. So this is a hierarchical page table, which is a simple technique wherein we break up the logical address into multiple page tables such as this. Now another approach that can be used is what we call a hash page table, and this approach is used to handle address spaces larger than 32 bits, with the hash value being the virtual page number, wherein each entry in the hash table contains a linked list of the element that hashed to the same location to handle collisions. And each element can contain three fields: the virtual page number, the value of the map page frame, and a pointer to the next element in the linked list. So how does it work? So it works like, for example, if the virtual page number in the virtual address is hash into the hash table, the virtual page number is compared with field 1 in the first element in the linked list. So if there is a match, the corresponding page frame or field 2 is used to form the desired physical address. But if there is no match, for example, subsequent entries in the linked list are searched for a matching virtual page number. So basically, this technique or this algorithm allows another approach to map the logical address coming from the CPU to its physical address. Alright, so we will, but in our later topic, we will just discuss the paging algorithm. So we are just presenting the other techniques or the other approach. Now another approach is what we call the inverted page table. Rather than having each process keep a page table and track of all possible logical pages, we will track all physical pages, and there will be one entry for each real page of memory, and each entry consists of the virtual address of the page stored in that real memory location with information about the process that owns that page. So this process decreases memory needed to store each page table. However, it increases the time needed to search the table when a page reference occurs. So use hash tables to limit the search to one or at most few page table entries. But how do we implement the shared memory? Solution is there should be a one mapping of a virtual address to the shared physical address. So again, this is an illustration of the inverted page table architecture. It is also a way to map the logical address coming from the CPU, which maps the physical address to the physical memory. However, in this case, we will notice that these inverted page tables require an address space identifier. So this is stored in the page table. This is called the address space identifier, or the PID. And since the table usually contains several different addresses space mapping physical memory, and storing the address space identifier ensures that the logical page for the particular process is mapped to the corresponding physical page frame. Alright? Now, a process instruction or process instructions and the data they operate on must be in a memory to be executed. We all know that. However, a process or a portion of a process can be swapped temporarily out of the memory to a backing store. We call it the backing store. And then brought it back into the memory for continued execution. So you will notice, I think this is the figure, wherein the swapping in and the swapping out happens, and swapping makes it possible for the total physical address space of all processes to exceed the real physical memory of the system. So it increases the degree of multiprogramming in a system. The standard swapping involves moving the entire processes between the main memory and a backing store. And the advantage of standard swapping is that it allows the physical memory to be oversubscribed so that the system can accommodate more processes than there is actual physical memory to store them. Most systems, including Linux and Windows, they now use a variation of swapping in which pages of a process rather than an entire process can be swapped. And this strategy still allows physical memory to be oversubscribed but does not incur the cost of swapping entire processes, as presumably only a small number of pages will be involved in swapping. In fact, the term swapping generally refers to standard swapping, and paging refers to swapping with paging. So a page out operation moves a page from memory to the backing store, and the reverse process is known as page in. So swapping with paging is illustrated in the figure. This is the figure. This is the swapping with paging, wherein we will see the subset of pages for processes A and B are being page out and page in respectively. So we will see in the next module the swapping with paging works well in conjunction with the virtual memory, because we're talking about virtual memory on this particular topic. Now, how is swapping done on mobile systems? So most operating systems for PCs and servers, they support swapping pages, but in contrast, mobile systems typically do not support swapping in any form. Mobile devices generally use the flash memory rather than more spacious hard disk for non-volatile storage. So the resulting space constraint is one reason why mobile operating system designers avoid swapping. So that's the reason. Other reasons include limited number of writes that flash memory can tolerate before it becomes unreliable, and the poor throughput between the main memory and flash memory in these devices. So instead of using swapping, when free memory falls below a certain threshold, for example, the iOS use or asks applications to voluntarily relinquish allocated memory. The read-only data such as code, for example, are removed from the main memory, and later on they are reloaded from the flash memory if necessary. Meanwhile, the data have been modified, such as the stack, are never removed. However, any applications that fail to free up sufficient memory may be terminated. Alright? It can be terminated. For example, before the terminating happens, like for example in the Android apps, it writes its application state to the flash memory so that it can be quickly restarted. So because of these restrictions, the developers for mobile system must carefully allocate and release memory to ensure that their applications do not use too much memory or suffer from memory leaks. Okay, in summary, we have learned from this chapter in our module 4, we learned that the memory is a very important component and very central to the operation of the modern computer system, which is composed of large array of bytes, each with its own addresses. And one way to allocate an address space to each process is through the use of base and limit registers. So the base registers holds the smallest legal physical memory address, and the limit specifies the size of the range. Now we also learned that binding symbolic address references to actual physical addresses may occur during compile, load, and execution time. So an address generated by the CPU is known as the logical address, which is what we call the memory management unit. The memory management unit translates the physical address in memory. So one approach to allocating memory is to allocate partitions of contiguous memory of varying size, and these partitions may be allocated based on 3 possible strategies, and we call those first fit, best fit, and worst fit. In modern operating systems, they use paging memory or paging to manage the memory, and in this process the memory is divided into fixed size blocks called frames, and the logical memory into blocks of the same size called pages. Now when paging is used, a logical address is divided into parts: a page number and a page offset. So the page number serves as the index into per process page table that contains the frame in physical memory and holds the page, and the offset is the specific location in the frame being referenced. So a translation look-aside buffer is a hardware cache of the page table where each TLB entry contains a page number and its corresponding frame. Now, in the last part, we studied about swapping, which allows the system to move pages belonging to a process to disk to increase the degree of multi-programming. So that's it for our topic. Thank you for your participation and for your attention.